All right. Hi, everyone. Welcome into the session. We are going to wait for a couple of minutes for everyone to join in. Thank you so much for being here today. We will just start off, as I said, in a couple of minutes. And feel free to let us, know with emojis over here if, how are you finding the conference today? Welcome to everyone who's joining in from across the globe. Great. Thank you so much, everyone. Once again, my name is Kavya. I am Director of Product Marketing at TestMe and I'll be your host for this session at TestMe Conference. Good to have you all with us today. A quick ask before we start: please make sure that you're, posting the takeaways on LinkedIn or X. Tag us, the speaker, that is Mahesh, and use TestMeConf so that the rest of the community can also follow the conversation that's happening. And if you have any questions during or after the session, feel free to drop it in the Q&A box so that we can basically take it up at the end. Let's get started with today's session. Most of the attention in this field, of course, goes to model architecture and post-training recipes, get some of what's left over at times. But the environment, what the agent actually practices on, how its work gets scored, or which tools it can reach for, gets a lot of times far less attention. An agent trained on a single turn questions has a hard time holding state across a multi-step workflow, for instance. So the question on the table is, what makes an RL environment good, and why should teams building agents be paying as much attention to it as the model they start from? So today we have Mahesh Sathiamoorthy, who is the co-founder and CEO of Bespoke Labs, who was previously at Google DeepMind. Bespoke curates data and builds RL environments while doing post-training itself. So join me in welcoming Mahesh. Mahesh, thank you so much for joining us today. We are very excited to hear your talk on why RL environments are all you need for building agents. So without much delay, over to you to take up the stage.
Thank you, Kavya. Let me present. Hope this is visible to everyone, right? Great. So I'll get started. It's my pleasure being here, and today I'm having this provocative title of "Oral environments are all you need." Right. So with the agent era, it's lot of people are excited about a lot of things, but I want to kind of share my perspective of how to think about reliability and improving these agents with a view towards data. And my name is Mahesh Sathiamoorthy. I'm co-founder and CEO here at Bespoke Labs, and uh, previously I was at Google DeepMind. And Bespoke Labs is like it's a data research lab. We are a Series A startup. Our goal is to help enterprises and the labs who are post training, and we basically work on the data aspects, and we ship RL environments. So I'll actually talk about what these RL environments are pretty soon. But what we do today is we do a lot of research in this area of the environments, and we ship these environments to the labs. So when you see the models are improving, there's a lot of work going into, of course, post training, but also curating the right environment. So we have been doing a lot of that work. So let's get started. So what's the problem that at least the enterprises are facing today, right? So there has been a lot of talk about superhuman agents which are able to solve decades old math conjectures but failing in production. There are coding agents that are able to kind of give write tens of thousands of lines of code, but when deployed in production, we are not seeing impact in revenue. So why is this happening today? In fact, interestingly, people are also talking about maybe pulling back agents from production, right? So why is this happening, and what can we do about it? This is kind of a way of thinking what's happening. So at the end of the day, it's about the reliability, right? So you have a specific task in mind for which you have built your agent, but the agent is not reliable for that particular task. That's why it's failing. So what's happening is that the frontier models, frontier agents, are trained on specific set of data and RL environments, and this is very different from the kind of distribution of tasks you have, right? So what they are doing is they're curating all these different environments for, say, writing, or data for, say, writing poetry or writing code, or doing taxes and whatnot, but they don't have access to the kind of tasks you are facing in your production. So unless you ship those to the labs, which you probably don't want to, they are not going to be able to train on this distribution. Of course, what they are doing is they are collecting more and more of all sorts of data to be able to encompass this distribution here. But what that also means is they have to also create larger and larger models, and invariably the token pricing, the token cost is going to go up. So with over time, what people are also already seeing is that the model prices are going up for improved reliability, right? So what can we do then to have agents that are much better on your tasks and on the distribution or the kinds of tasks that you have? So that's the view with which we want to kind of address this question. So before I actually tell you how to do that, let's think a little bit about how to again think through how to solve this particular issue. So if you remember the 60s, which a lot of you may not remember, I myself don't know, but what I've heard is that in the 60s, expert systems were actually being built, and people actually thought AJ is right around the corner. But what was happening is really intelligence was codified as a handwritten if-then rules, quite a bit of it. It's AI in codes. This kind of AI expert systems were built. For example, there was this chatbot called ELIZA, which initially they people thought it's doing well, but they realized very quickly that it doesn't generalize. It's basically having following a script. So people got soured on AI at the time, and then we had what's called AI winter, where people didn't invest into AI as much. But what got us out of this AI winter was deep learning, right? Where we perfected this ML recipe, where there was neural networks that were worked on, and they were becoming deeper and deeper. So ultimately what happened was that we were able to replace these handcrafted if else kind of features with models that are learning on the fly, not on the fly, but learning from data. So the ML recipe, this has been kind of something that people or understand this very well. We have lots and lots of us have deployed this kind of recipe in production, for example with recommender systems and whatnot, where you curate some data, examples for the task you have in mind, and then you train a model, and it learns the distribution for the kind of task you have in mind. So the bitter lesson, there is this famous essay called Bitter Lesson. All that ultimately what it says is that methods that generalize, that leverage compute, generalize far better than handcrafted methods that use human intuition. So ultimately, the recipe again is you curate data and you apply compute on a specific model, and it learns the distribution. And this recipe has also worked pretty well for even for LLMs. So the previous one, it's 2010s and so on. We did a lot of this work, and with LLMs, the data has been like at least the previous generation of chatbots has been the SFT data. For example, you have prompt and a response, a question and how to answer, and these are much more complex LLMs. They have been scaled up, a lot more compute. It's learning all sorts of distributions. And now, what about the recipe for agents, right? What is agent data? What is, we can talk about what exactly is an agent. And again, the question is, how do you learn? Then if we apply compute, then it should learn the distribution of tasks that the agent data captures. This is pretty much the recipe that even the frontier labs use, right? Obviously, there are so many details here, but At the end of the day, it's leveraging compute on curated data. So let's first understand what data is for agents. We go from prompts and responses to what's called environments and verifiers. So with LLMs earlier, where we had them to, we would ask questions and they would respond, it was a lot more about knowledge. Right now it's a lot more about action. So the agents are actually doing action in an environment. When you open Cloud Code, it has an environment that it has access to, your laptop and this folder, and it's doing some action. And in order to train an agent like Cloud Code, you curate lots of these environments, and then you have to also have a way to verify, right? So in the case of SFT and the traditional machine learning model, you always have a label. In this case, it's a verifier that says whether an agent actually solved the task that has been given to it in the environment or not. So this is the RL environment that I've been talking about. This is kind of, a lot of people are now working on this, where the RL environment is capturing the world that the agent acts in. So in your case, if you have some sort of a system, production system, you may want to kind of build a RL environment that's mimicking the production system that you have in mind, so that it becomes like a contained environment where you can do all sorts of training and eval that I'm going to talk about. And the verifier, as I was saying, is whether in your case the agent solved the task or not. Let me give a very quick example. So an RL environment can be a collection of databases and DBT transformations, mimicking what's happening in an e-commerce store. For example, if it is storing data in Snowflake. And you could have a task that says calculate the revenue in Q1 of 2026. So you have this RL environment, you drop the agent in it, it has access to, it's able to read the files, it's able to read the databases, it has access to some specific tools, and then it has to run queries, do some math, write a Python script or whatever it is, and get you the answer. A lot of times we don't necessarily care about what exactly it's doing, as much as we care about, okay, did it actually do it or not, right? So this is an example of RL environment. This is, you can curate lots of this, again, as I was saying, corresponding to the use cases you have in mind. There are standard tooling that is now emerging, for example, what's called Harbor format or Harbor framework. And we have also been, of course, building lots of tooling around this. So now we understand what is data for the agent recipe. And let's see what is an agent, and let's see how we can apply compute on an agent on this data to learn the distribution. So how do we apply compute? So agent, in simpler terms, is basically a LLM that's dropped in, that's wrapped around a harness, and it's given a specific goal of, okay, here is what you have to do, right? So, so that's the uh, prompt. So these are three components to an agent that we can think about optimizing each of them. In many situations, we are taking these as frozen entities. For example, we can use Opus 5 here, either Cloud Code or Pi or Open Code or some other harness is there. And now most of us iterate a lot on the prompts. So again, if we recall the better lesson, what it says is like human driven intuition or hand authored agent behavior is suboptimal. We need to apply compute. We need to kind of use scalable methods that generalize better. So what we today do, it kind of works in some cases, but as we build more and more complex agents, it is becoming harder and harder for us to deal with, even say updating the prompts, right? So in many cases, what I've seen is people are building complex agents with multiple sub agents and whatnot, and specifying the prompts in many places, and what you make one change in one place, and then like a whack-a-mole, something else goes wrong in a different place. So there needs to be a systematic method. So let's see how we can kind of apply compute in all of this. This we yeah, this is one of the so this is kind of what most of the labs do, which is they are training the LLM itself. It's called a policy. So there are hundreds and hundreds of papers written about it. This is basically what's called post training, where you take a pre-trained model and now you are doing SFT and RL on some specific set of data. Again, if you remember the distribution I was talking about, there has been lots and lots of data and RL environments curated here, and now the frontier labs, the next is to kind of uh, do RL runs and SFT runs here. So this is one of our papers where we also talk about how we do data recipes as well as training for this. This is still a little harder, but our goal is to make this easier and easier. A lot of company, like of course all the frontier labs do this, many neo labs are doing this, and then AI native companies are starting to do this. And of course, I will give you one example of where we did this successfully with an enterprise. So that's how you apply compute, right? You literally have GPUs where you are training these models. And now, how do we apply the better lesson to have scalable methods of improving the prompts? So how do we? So one of the techniques is called GEPA. So in JEPA, what happens is you are using other LLMs to reflect on the failures of the agent or the model that you're trying to optimize, and that is doing the iteration. There is evolutionary algorithm that gets used, but at the end of the day, if you think about this, it is using more compute in the form of tokens and sandboxes and whatnot to iterate on the prompt. So there is search happening in a bit more of a systematic manner that gives rise to way better prompts, right? So that's kind of one of the methods of um, optimizing the prompts. So this technique called JEPA is now widely quite broadly used. There is a standard library that you can use it. You can use, and a lot of people are using this to kind of take existing agents and they curate data and then kind of make it way better. And then there is harness also. So today, most of us are using frozen harnesses, but there is actually no real reason to just go with frozen harnesses. There is now work that is happening where people are updating the harness as well. This I think is going to be a lot more of of work that will happen in the research community and then comes into the enterprises as well. So this is one example of work that actually optimizes harness, but there have been recently a lot more uh, work that is happening. So I will also talk about another example in the case of Snowflake, where by adding specific tools for the specific tasks that they have in mind, they're able to improve the reliability of agents that they are building for their use cases by updating the harness. Again, saying this can be done manually, of course, just like we are iterating on the prompts, but the similar techniques as here where we apply evolutionary algorithms can actually help us iterate on this um, harness code, for example. So far we have seen what is data and what's an agent and how to actually apply compute on the agent. So how does this all relate to you and what is common here, right? So compute is quite accessible. The optimizers in the case, what I was saying is like this library, for example, JEPA, post-training, SFT libraries, RL libraries, they are all kind of fairly well understood and commoditized. But the only scarce ingredient is this RL environments. So even with the labs, this is something that everything else is kind of standardized. This is one thing that they are curating with help from external partners. And for enterprises, the one of the specific things that I'm trying to convey is that this is something you should pay a lot of attention to when you are building your agents. Everything else is somewhat democratized and well understood. This is your In many cases, again, your task is your recipe, your IP. So how can you kind of, curate that, those RL environments that capture your use cases, and then build agents on that. So, as I have actually talked to you about, with RL environments, you can do SFT and reinforcement learning itself, or you can do prompt evolution with JEPA and harness evolution as well. But there is also, they're also very valuable in also doing evaluations as well, right? Actually, let me give a very concrete example from Snowflake, where this is Sridhar Ramaswamy. He is the CEO of Snowflake. He used our data. Basically, Snowflake worked with us where we curated RL environments for data engineering. So data engineering is a very, very big use case for Snowflake, and they are training their agent just like Claude Code. They want to build their own Cortex agent, which is good at using Snowflake and doing all these data engineering tasks, right? So this is a very concrete use case. Again, this is a slightly different distribution compared to what the Cloud Code has been trained on. So again, if we think about this, how do we make a better agent for, in this use case? It all starts with RL environments, and we curated some of these RL environments for them. And with that, they are already able to do systematic evaluations, right? So this is one of the viral threads, where they talk about how GLM 5.2 and Opus 4.7 compare on the specific 103 RL environments that we captured. Again, if you remember the use case, there are of computing the revenue, there are similar tasks in these RL environments. And once you have access to them, you are able to systematically check what the success rate is for different models, what the token usage and the costs are. And also it gives you lots of different insights on, oh, GLM actually does a lot of verification before it gets to the answer. And then you can also do failure mode analysis. You can look at the trajectory, you can kind of understand what the failure modes are and so on. So it becomes a lot more of a systematic process of understanding what the agents are doing and then improving them. So now, for at least for Snowflake, once they have this kind of understanding, they can take this as an example, this open source model, and with more data they can either do the post training, as I was saying, right? Or they can evolve the prompts, or even the harness, as I was mentioning, right? So in their case, they can add more tools to, do some sort of query runs, to as a way of verifying. All of that helps build better agents. The other example I want to talk about, which is a very concrete use case, is from Intuit. There is a paper that we also wrote about this recently. So Intuit has this Credit Karma product. So you can install this app, and in this app, you can it can recommend a specific credit card to you based on, all your credit usage and credit history and so on. But more critically, they want to kind of explain to you why a credit card has been recommended. So this is a very concrete use case, and this was, kind of on the other side of the 50% that I talked about right earlier, where it wasn't working very well, in the sense there would be hallucinations. So there will be maybe the credit card name may not be written in the right way, or some interest rate is there is a typo, or it offers a 0% interest rate and whatnot. Again, if we think about it, this is happening because this kind of use case has not been there in the training data for the frontier LLMs. So there is a new task distribution. So how do we curate that, and how do we train a model for that, right? So as simple as that. So this was something that was launched, and lots of issues, meaning previously they had launched this before we worked with them. lots of issues around, as I was mentioning, hallucination, incorrect numbers, and whatnot. And the latency was also high, so this was affecting the user experience. So now, what we help them is to work with them to do curate the data and optimize an agent, a model for this specific use case. And this is a fairly widely used product with more than 100 million users. And after doing this post training, which involved SFT, and we also did JEPA, so this particular thing, we were able to improve the agent, the model quite substantially, that we actually started seeing that it didn't have the kind of hallucinations that were there. Right, again, the hallucination is a major problem because it's compliance violation. Of course, not only the credit card companies are upset, but even based on government regulations, you don't want the compliance issues. And since we actually took an open source model and trained it, the cost was way less, and the throughput also became more, and the latency was reduced. So overall, it was a much better experience for the users and for Credit Karma itself, right? So we went from that previous 50% where things are struggling to the other 50% where we were actually able to deploy something to production, which is served to hundreds of millions of users. So again, all of this is great. So far, what I've told you is like there is, what's something called RL environment. I've told you that you can use those to do evaluations, SFT, prompt evolution, harness evolution. But what should you be doing concretely? I've also given you some use cases, but let me kind of mention a few things, right? So if you remember this diagram, so again, existing models are here. You want your model to be good at these tasks that your distribution cares for. So how do we move this? So first, think of becoming a RL environment engineer in the sense that you have to, as you're building this in agents, think about how do you focus a lot more on the data and the RL environments. So, it- as I was saying, for LLMs, you kind of the ML recipe is you write the training data and the model um, gets trained using GPUs, and you're able to fit the shape of the task. And for agents, you have to build the RL environments, you train, evolve, and whatnot. You fit the shape of the task. So far, most of us have been prompt engineers where we manually fit the shape of the task by writing the prompts. Or sometimes we apply we wear the hat of a AI engineer where we are kind of manually training. But it so happens that, as I was saying, we can optimize, we can automate a whole bunch of this using things like JEPA. And now even agents are actually getting better at just kicking off post training runs and evolution algorithms and so on. So the thing that most people should be focusing on, or eventually will become, is like they will be curating these RL environments specific to their use cases. And once that is done, all of this is taken care of in a large essence, right? So the job now becomes how do you kind of build the substrate or the framework so that you can capture this data, and then you can apply compute so that you fit the shape of the task. So the other thing that I want to mention is building the data flywheels. So one of the things that happens is like you kind of want to build these environments, you are maybe training them and you deploy, but you can actually look at the trajectories, you can actually see what's happening, and you can understand where your agents are failing, and then curate more environments to tackle those failures, right? So this is the true essence of what we want to achieve as agent builders, because this way we have a feedback loop that helps us continuously improve. So if you take a frontier model, frontier agent, and if you're deploying it, it's kind of most of the time it's static, right? It's like performance is not improving over time. You're not, sometimes of course you can manually update a few things here and there, but essentially what you want to get to is this feedback loop. Whether you are taking frontier agent or an open source agent, you want to establish this feedback loop so that you can curate the, more and more of these failure RL environments corresponding to the failure use cases, and then keep patching them. So that's what will let you go from some model that maybe, is not as good as a frontier model, and then improve it over time, right? So this is with post training, or you can also start with the frontier agent and then do evolutionary algorithms that can keep improving over time. So this is the promise of post training. This is the promise of post training, in that it can reduce the cost quite substantially, and improve the ROI. And since you have set up a feedback loop, it kind of keeps improving on your use cases. So with that, I kind of want to conclude by saying that RL environments and compute are kind of all you need. Remember the better lesson, and invest in data, become a RL environment engineer. Think about what are the, what agent you're deploying in production, how to kind of make RL environments out of that, and then set up this data flywheel. With that, I am happy to take questions.
Thank you so much, Mahesh. Really appreciate that insightful session. And I can see that we have a couple of questions from the audience coming in. One second. So let me just take that real quick. Okay. So the first question is, how do you test rare but high impact agent failures?
Yeah, that's one thing that happens today is like people deploy and then, kind of see what production failures are happening. So the other aspect is, again, this is the example I was giving in the Snowflake example, right? Where you want to kind of not deploy an agent and then wait for what kind of failures are happening, but sometimes you want to kind of uh, catch this early on, right? So that was, again, in the ML place, in the ML recipe, we always had train data, eval data, test data, and then only we do A/B tests on production. So the whole point there was we curated data relevant to what will happen in production, and then we would test and we would actually train a model and test how well it's doing. So similarly, you want to kind of curate environments that are as similar to as the production that you're going to see, the use case you have in mind. And then once you have that, you can actually, what happens is you can curate these environments, you can drop the agent into that environment, let it do its thing, and you will get the trajectory, right? So okay, this is the first step, and so on. And you can actually use other LLMs to analyze these trajectories. You can kind of cluster them and whatnot, and then understand failure modes. So this is something we actually do a lot with with frontier agents. And this is also the whole point of benchmarks, is like it actually captures, in some sense, it's telling you, okay, this is the task and this is the percentage. The As an example, terminal bench, if an agent is 80% good in terminal bench, it means that you can analyze the failure modes for the remaining 20% and understand how these agents are failing. So there is some art to this, but you can make this a lot more systematic, and use that to understand the failure modes that will happen in production.
Thank you so much. The next question is from Abdul. When should soft benchmarking versus hard data benchmarking apply to AI agents, LLMs, and similar tools?
Sorry, can you repeat that again?
Sure. So the question is, when should soft benchmarking versus hard benchmarking apply to AI agents, LLMs, and similar tools?
I see. So I don't know what the difference is between soft.
Yeah.
Mhm. But
Perhaps you could. I'm not sure if the attendee could perhaps add more details, but yeah.
I can try to yeah. So soft versus hard benchmarking. So I assume soft benchmarking is like benchmarking you do before what's happening in production, and then hard benchmarking is like maybe actually like looking at the production failures, right? So I think this kind of relates to the previous question. So you want to kind of avoid as much surprises in your hard benchmarking and production failures by shifting all the work to the soft benchmarking, right? So as long as the soft benchmark is similar to the tasks you see, again, uh, you want to curate as many tasks
Mhm.
as possible for your benchmarking for your specific tasks you have in mind, so
Yep.
that you can understand systematically how the agents are failing. So that would be your soft benchmarking. That way you are avoiding surprises. If not, what's happening is you have taken a model that's trained to this, say, this distribution or this distribution, and then you are looking at failure cases in production, which would be the hard benchmarking.
Thank you. Mahesh, the next question is when scaling to 100 million plus users with lower serving costs, were any trade offs made regarding model size, context window length, or guardrail complexity?
Right. Sorry. This particular example.
Mm-hmm.
Um, right. In this case, the initial model was a GPT. I'm forgetting the specific version of the model, but we went from that to a llama-based model. So this was work done some time ago. So the model size was quite substantially different, and that this is again a very good example of why bespoke models or custom models that fit to your distribution will work well, right? You don't necessarily need all the intelligence in the world in a specific model that's has to only recommend credit cards, right? So once you have the train data, eval data, you can actually this becomes a evaluation problem. You can train models of different sizes, and then you can do like a plot of, okay, this is the cost, this is the ROI. Maybe I can get this, forget about all the different dots, but maybe we go from here to say here by post training. So you can take one model, maybe you take a slightly bigger model, and maybe it gets you here, right? So then you can have a good understanding of, okay, do I is this data point better than this? So maybe in your use case you might realize that this particular data point is better than something else, because it's way cheaper to deploy, and you're getting almost 80 to 90% of the impact that model larger model that gives you. So that's one thing. And then I think the context length was also mentioned in the question.
Yeah.
Again, this is the advantage of post training, is you can, instead of having, so this was literally the advantage, right? So in this case we had to have, with GPT you have to have a very very long prompt that lists all the rules, all the compliance issues. So that was driving the context length so much that it was actually increasing the latency and I guess the hallucinations. But now all of this knowledge is now fed to the model, it's actually learning it, so the weights have been updated, so you don't need a long context anymore. So that kind of helps reduce the context length, and therefore also the latency, right? Of course you have a smaller model but also a smaller context. So the attention length, since it increases by O of n square, you don't need to worry as much. So the latency actually decreases. And then the guardrails was something mentioned, but in this particular case, we needed a lot more guardrails before, and now since we are able to check that the models are actually way better in complaints, you don't need
Mhm.
as many guardrails.
Thank you. I could perhaps do pick up one more question, which is from Paul. How does memory overhead scale when running thousands of environments simultaneously in RL environments? I know that you touched upon it. So yeah.
Yeah, actually, it's an interesting question. So, um, this is I feel like it needs a longer answer, but basically we are building all sorts of new infrastructure that I believe people will have. Lot of the agent development work will go towards using these kind of infrastructure. But to specifically answer the question on like thousands of RL environments, what happens is then you need to run all sorts of sandboxes, right? So these RL environments, or um, most of the time these are virtual machines that you want to spin up. So you want to be spinning up thousands of these virtual machines, so the CPU cost becomes kind of real. And then there is infra needed to make sure you can snapshot if an agent fails halfway through, maybe you want to kind of recover. So all this other infra is built to manage, track, snapshot, restore, whatnot. So you have probably seen a bunch of these sandbox companies that are popping up. Of course, E2B, Daytona, Tensor Lake, and whatnot. So we also have our own infrastructure. But at the end of the day, as we do a lot of these RL runs or even evaluations, we have to spin up these sandboxes, which consumes both memory and CPUs. But this is a trade-off you make, right? Like to kind of systematically improve your model, so that by throwing more compute in a sense before you deploy it in production. Cool.
Thank you so much. That brings us to the end of the questions. I just give me 1 second. I'll just remove this from the screen. Thank you so much, Mahesh. Really appreciate the time that you have spent today. Uh, we I hope that our audience has been able to gather a lot of insights from the session today. I would request that to the audience, please reach out to Mahesh if you have any questions, and feel free to share about the learnings that you've had in today's session with the larger community. We are also running a social media V challenge, so would be great if you can participate in it and share the learnings that you had today. Mahesh, really appreciate you spending the time and giving us, nearly an hour. Um, Thank you so much. It has been a super interesting session to begin with. The other thing that I wanted to remind the audience is that all the sessions will, of course, be available on our YouTube channel. So revisit them at any time. And before we move on, once again, we do have participate and win and a couple of other challenges running for you. So feel free to again be a part of it. Awesome. Thank you so much, Mahesh. Really appreciate it. Have a great rest of the day, everyone. And to the audience, we have more sessions lined up for you. So please feel free to join it. Thank you.
Thank you.